PV is equal to nRT homework. So that's all good. And we're just going to keep kind of building on that. Now we're going to combine the ideal gas law equation with stoichiometry. Why not, right? So what I would suggest in this sort of problem is to basically what I've been doing other times in the semester, pulling out from the text and putting under the balanced equation. So it looks like this. Let's just kind of start from here. What volume? So I find my H2 and I say V is equal to question mark. What volume? That's supposed to be a question mark. Equals question mark. What volume of gas? And then it gives the other couple of things about the gas. It gives the temperature is 22 degrees Celsius. So I'm going to put that under my H2. I'm going to put T is equal to 22 degrees Celsius. Now, you're in the habit of fixing that degrees Celsius to Kelvin, which is great. It goes ahead and also gives us a pressure for the hydrogen. So P is equal to 1.00 atmospheres, which of course, okay, we don't have to convert that, so that's fine. And it doesn't give N, but it gives mass. So I'm going to go ahead and say N is equal to, and I'm going to put 2.50 grams of H2. So it's under H2. So we can actually convert these grams to N. So that's easy. So bottom line is we have 3 of our 4 variables, and we can get to volume. So the problem goes on to say what volume of H2 gas can be produced using, are you serious? Deb Nevitt. I can't believe I did that. Okay. Oh, wait, go back. Okay. Sorry. Reading it again. My volume was right. Volume is equal to question mark. My temperature was right. My pressure was right. But what's not right is the mass. That mass goes under the zinc. I was like, that doesn't make sense. Okay, I'm feeling much better. Notice that I'm going to put N over here. Oh, goodness. I got double vision here. I'm going to put N over here, and I'm going to put question mark. We don't know moles of H2. Grr. So now this is making more sense. Here in a minute, you're going to see what the slides tell you to do. Is basically, you can get to moles of zinc, no problem, using the mass and the molar mass of zinc. Then you can use stoichiometry to get to moles of H2, no problem, using stoichiometry. And then finally, when you have those moles, then you have 3 of your 4 variables. You have N, P, and T, and you're looking for V. So, final answer. So we need to get to moles of zinc. By the way, the HCl was in excess, so that's all good. So we use a periodic table, look up the decimal number for zinc, and it's 65.39. So we put 1 mole of zinc over 65.39 grams of zinc. Grams of zinc cancel, we're left with moles of zinc. We use that as a first term in the next stage. So we put 0.0382 moles of zinc over 1. And then we use the stoichiometry of the balanced equation like we've done earlier. We have, 1 mole of H2 for every 1 mole of zinc. So that's kind of where that ratio came in from, 1 mole of H2 over 1 mole of zinc. Our moles of zinc cancel. Now we have the N term under the H2. So that's 0.0382 moles H2. I can do that math. So now we can go over, and we're going to use everything under the H2. And we're going to rearrange P equals nRT, solving for V. We divide both sides by P, and this is the equation we're going to substitute into. Let's go ahead and fix your temperature by adding 273. So 22 plus 273 is 295 Kelvin. Now we're ready to go. So volume is equal to nRT divided by P. So volume is equal to N, which is 0.0382 moles. R, 0.082058 liters atmospheres per mole Kelvin. T, we said, was 295 Kelvin. all over 1.00 atmospheres. And I've gone ahead and showed you the build. When you multiply that all together, you get a value of 0.925, round to 3 significant figures, which is what you're allowed. Unit-wise, looks like moles cancel, kelvins cancel, atmospheres cancel, and we're left with units of liters in the numerator, so which is great. Perfectly great units for volume. And that's it. That's the answer. All right, let's do another one. I'll see if I can concentrate a little more, getting my information right with the right thing. All right, so volume of hydrogen gas is 125 liters. So I'm going to find my hydrogen. I'm going to say V is equal to 125 liters. And it goes ahead and gives me the temperature of the hydrogen gas, already in Kelvin for us, yay. And it gives a pressure, okay, 0.783 atmospheres for the H2 gas. It gives us, it says nitrogen is in excess, which is great. And so N wasn't given, number of moles aren't given, but guess what? I can get number of moles from volume, temperature, and pressure. Now, actually, that's going to be where I start. And then the question in italics down here is how many liters of NH3, so volume is equal to question mark liters, how many liters of NH3 can be produced if the NH3 is at STP, standard temperature and pressure. Very good. Okay. So I'm going to go ahead. Do you guys remember what the temperature is for standard temperature? It is 0. Yep. 0, what are the units? Yep, 0 degrees Celsius. Perfect. What is the standard pressure? It's not 1 bar, 1 atmosphere. Yep, 1 atmosphere. I'm going to go ahead and throw in a few sig figs. 1.000 atmospheres. Cool. And of course, N is question mark. But it's kind of like titration problems, I think, because notice that we have, like I said, enough with the H2 to knock out N, right? And then we can use stoichiometry to get to that N, right? And then we've got 3 of the 4 required variables for our NH3, and we can get to this. So let's go ahead and do the first step, focusing on the H2. So it looks like this. So for the hydrogen gas, we're after N. So if we rearrange P equals nRT, we're going to divide both sides by RT. That gives us N is equal to PV over RT. Again, this algebra, it's so easy to make a mistake with this, unfortunately. So let's substitute in what we know about the hydrogen gas. The N then is equal to, in the numerator, oh, my technology is just being silly today. You guys got it all there, but I don't have it here. Isn't that crazy? This little box is everything that I wrote underneath that H2. So in the numerator, we have pressure, 0.783 atmospheres, also volume, 125 liters. And in the denominator, we have RT, 0.082058. And units of R are liters atmospheres per mole Kelvin. And then also in the denominator, we have the temperature, the 298 Kelvin. So looking at the units that cancel, let's see. I'm liking liters cancel, Kelvins clearly cancel, atmospheres cancel, and here's where we have units of moles, the inverse of moles in the denominator, which is equal to moles. So 1 over moles in the denominator. So the units are moles. Round to 3 significant figures. I got a nice even round number for the moles of hydrogen gas. 4.00 moles of H2. So again, the strategy now is we said we're going to use this N in stoichiometry to get to the N of the NH3, the number of moles of NH3. I think we could. Okay, so 4.00 moles of H2, and then the stoichiometric ratio that we've used like before, okay, we have 2 moles of NH3 formed for every 3 moles of H2 consumed. So that's where that comes in. So rounding it to 3 significant figures, of course there's an exact relationship with that stoichiometric ratio. So we're allowed 3 significant figures, and I get 2.67 moles of NH3. Now here's where we have a choice. This, if I was doing it, I would forget the next thing I'm going to show you. I don't mean like I would just forget it. I'm like, I would literally just forget it. Okay? So you could substitute that in back in under the NH3 stuff and solve for volume. Or you could remember that neat little trick that we talked about, STP trick. Remember that beach ball thing I brought in, which I don't really think it really was 22.414 liters of volume. But if a gas such as NH3 is at standard temperature and pressure, then the volume is set. The volume for 1 mole is set to be equal to 22.414 liters. So we have this 1.000 moles is equal to 22.414 liters. Okay, so that equivalency actually can be used as a conversion factor. So I'm going to show you. We can piggyback off of that moles. That moles will be your first term. And then we can use that equivalency at standard temperature and pressure as a conversion factor. So if we go 2.67 moles of NH3, we want moles to cancel, so we'll put 1 mole in the bottom, and we're after volume, so we'll put 22.414 liters in the top. Now this is only at standard temperature and pressure. So this is another one of those chemistry problems where you have a couple of ways to work it. Either way would be fine. You should get the same answer. And like I said, I don't think of this 22.414 liters is exactly equal to 1 mole at standard temperature pressure. That usually doesn't. Okay. So we get 59.8 liters of NH3. Cool. All right, one more, and there's a twist to this one too. Okay, so let's go ahead and do like I've been doing, and I'll try to be careful about it. So dealing with the hydrogen, we're given the volume of V is equal to 25.0 liters. This just does not want me to do this today. Okay, let's see. Notice it gives the temperature. T is equal to 25.0 degrees Celsius. Whenever you're doing gas problems, you're like, oh, degrees Celsius, it needs to go to Kelvin, that sort of thing. And it also gives the pressure in units of atmospheres, 1.25 atmospheres. Okay. It doesn't give us the N. N is equal to question mark. It does say that the other reactant, that's hydrogen, the other reactant, nitrogen, is in excess, which is kind of nice. So any NH3 formed is driven by the amount of H2. So in italics is the question. So how many liters? So V is equal to question mark liters for the NH3. Now, this might seem like a little bit deja vu. The temperature of the product, NH3, is also 25.0 degrees Celsius, and the pressure is also 1.25 atmospheres. And they ask, they ask how many liters will be produced. N is equal to question mark. Don't know, right? Well, we could do it kind of like we did the last problem, where we have enough here to get to the N, and once we have the N, we can plug the N in here, and then kind of backtrack up now using these three values to get to the volume. We so can do that. But I'm going to show you this little trick. Oh my goodness. It kicks me off and I have to reconnect. This little trick is that if we look at the temperature and pressure, they are the same. If the temperature and pressure are the same, all we have changing are, or it's not really changing, but if the temperature and pressure are same, then the number of moles are directly related to the volume. So it looks like this. Since the volume and number of moles are directly proportional, we can go straight for the problem. We can basically link the, once we get to the moles of the H2, we can use this. Is that right? Oh, I don't know. Can't remember what I... No, we don't have to do moles of H2, sorry. Oh, grr. So we can take our ratio. This is our stoichiometric ratio we're used to. And instead of relative moles, it's relative volumes. And we don't really have to do much at all. All we got to do is take the volume of our H2, which was given, and go directly to the volume of NH3. It looks like this. That's the volume of H2. Insert our ratio, which looks like a stoichiometric ratio, and it is. And it's relating volumes instead of moles. So this came directly from the balanced equation. And that only worked because the temperatures and pressures were the same. So now liters of H2 cancel, we're left with liters of NH3. Voila! We are so done. Round to three significant figures, it looks like this. 16.7 liters of NH3. That's it. We could have done it the other way, which on a good day or bad day, I would do it the other way because I would forget how this works. Okay. So I just want to caution, and I think you guys all know you can't go straight for using the stoichiometric mole-to-mole ratio as a volume-to-volume ratio. You're not going to tend to do that unless your pressure and temperature are the same. Too many ways to work these chemistry problems. But one thing I do know is when I grade them, I'm looking for units. I have to see all the units. And on that last section of your comprehensive final, I'm looking for all the units. I think each problem's worth, what I say, 6 points apiece. So you lose points if you don't put units, and you lose points if you don't show all your work, and you lose points if you don't round correctly. But let's not think about losing points, let's think about gaining points.
If you get the wrong answer, show all your units, we still get points.
Oh my goodness, yes. If you show your units and you get the wrong answer and you showed how you got everything, that's your best bet. Oh yeah. That in any science class where you have a teacher who knows what he or she's doing, that's the way to get your points.
Yeah, our number has the 4 units, right? I keep forgetting that.
The 4 units. The R has liters, atmospheres per mole Kelvin.
Okay.
And remember that you get to bring something with you to the test, and I'd put that on there. Okay, definitely. So I decided in my desk today, I'm not gonna go through these problems. These will be due on Wednesday, but I'm just gonna push them out there. Wait, I think I was just gonna show you, but I'm not gonna like show you because they just look like this. 651. Cool. So, I mean, sometimes these hints, again, you might do them differently. Here's all the hints I have for the first one. And the second one looks like this. Here's all my hints. You know, take them or leave them. And the third one looks like this. Okay. So, again, I'm kind of a firm believer, and you saw me kind of mess up. So I'm kind of a firm believer to write my stuff, and you might write it down. You're like, well, that doesn't make sense. And you go back and you fix it. Okay. So on to the next part, partial pressures. I love partial pressures. I love gases. Okay. Partial pressures make sense. You remember, did I talk about the other day, if you're in a swimming pool, there's no like non-P section and a P section for little kids? No? Oh, I must have. My intro students are doing gases right now too. One of the things about gases is that they're mobile. They take on the shape of their container, they take on the volume of their container, and just like liquids, there's actually gases and liquids are both fluids, you know, and there's fluid dynamics and everything you study in engineering. But so yeah, they mix. And so actually in this section, we're going to talk about gas mixtures. Like in this room, it's mostly nitrogen. It's like 80 nitrogen and 20 oxygen. And it's not like segregated. It's like one big happy family. So we have a partial pressure of nitrogen and we have a partial pressure of oxygen in this room. Okay. So this is I like this kind of three images. They're kind of showing you. Here we have hydrogen minding its own business. And here we have helium minding its own business. Okay. Now remember we talked about the little weights are an indication of the pressure of the gas, because that little plate that the weights are on is mobile. It's like a little plunger thing. So here we have the pressure of our helium is 6 atmospheres and the pressure of our hydrogen is 2.4 atmospheres. I really like science because I'm not a words person. Notice that we use this convention of using like little subscripts to show what the partial pressure is. So the partial pressure of hydrogen would be P with H2 down there. Like, oh, that makes sense. The partial pressure of helium, okay, like that. So we also are given the moles. The other cool thing, these containers, they have the same volume, same temperature, same volume, same temperature. So now is sometimes the case, we're going to take both of those gases, we're going to admit them to a container that has the same volume, 5 liters, at the same temperature, 20 degrees Celsius. And now, of course, you see the red and the blue all swimming around in there. No P zones. There's no P zones here. Okay? They form a homogeneous mixture. Not so surprising. The pressure in here is higher. Okay? But specifically, notice how much higher it is. Okay? So this pressure actually, now it has what? See, I have 5 weights here. I have 2 weights over here. I have 5 weights here, and I have 7 weights there. The pressure in the first one was 2.4 plus 6.0. I'm looking at a pressure of 8.4. They're additive. I guess that's my point. I just think that is so cool. They're additive, and it makes sense. Okay, the moles, of course, are additive. I had half a mole there, 1.25 moles there. I have a total moles of gas there, 1.75. I just think that is so cool. That's the way gases are, and we're going to be talking about this with regard to partial pressures. So this actually kind of does the same thing, but instead of 2 components, there's 3 components. I don't say what the gases are, but we have gas A, gas B, and gas C. They're in these containers. We're going to put them all together in a container, a combined container over there at the left here in a minute. Notice that the volumes are the same, the temperatures are the same, just like we saw before. We have moles of gas A, gas B, and gas C. Okay, makes sense. At the top there, that's our cute little pressure gauges. Okay, and the pressure gauges up there are sensing the partial pressures of each of the gases that we're getting ready to combine. We could come up with the partial pressures of each using the ideal gas law equation. If you rearrange it, solving for pressure, pressure is equal to nRT over V. Now, the catch here, I guess there isn't necessarily a catch, But notice that actually the temperature and volume are the same. They are shared. Actually, they're going to be shared when I combine them too. R is also the same across the board. So bottom line is, if we go ahead and dump these three things into this single container with the same volume and temperature, the total number of moles will be the sum of the individual moles, right? And the total pressure will be, you know, what you might imagine. The example we saw a minute ago with helium and hydrogen, was it? We added up their two pressures to get their overall pressure, and that's exactly what we would do here too. And I'm going to kind of show you a proof as to what that total pressure would be. But the total pressure we can get by taking the individual moles times the R, which that's the same for everything. That's always a constant. The temperature and the volume are the same in all of these cases. So it's kind of like we saw a minute ago. I'm going to kind of take you through a proof here. Okay. So we know we can distribute that sum, the quantity Na, the moles of A plus the moles of B plus the moles of C, we can distribute it through this the product and the quotient. Okay, so it looks like this. We can distribute it back out into this. Okay, where obviously those individual ones represent the partial pressure of A, partial pressure of B, and partial pressure of C. We're finally building to something that's called Dalton's law of partial pressures, and here it is. According to Dalton's law of partial pressures, it's exactly what we saw a minute ago. If you have a mixture of gases, of course there'll be a homogeneous mixture, and the total pressure they exert is equal to the sum of their individual partial pressures. That's it. And sometimes, like Dalton's law of partial pressures, I'm like, really? I mean, anybody could have thought of that, I think, if you think of what gases do, but he proved it. So I guess we'll say give credit where credit is due. So let's look at Dalton's law of partial pressures a little bit closer. So let's take component A. Okay, we have a gas mixture. It could be A, B, and C. And component A, the partial pressure of A looks like this, where it's the moles of A times R times T divided by V. For the full mixture, the total pressure is equal to the total number of moles times R times T divided by V. Now, we kind of do this sometimes in physical science. We're basically going to divide one by the other. If we divide the first by the second, it looks like this. You're like, how would you do that? And why would you do that? Well, it's part of, I won't say chasing your tail, but it's part of making a point. So now you're going to see on the next slide, we basically have this ratio, which is the partial pressure of A divided by the total pressure, is equal to this ratio. But this ratio over here on the right, check this out. Of course, our R's and T's cancel, and our V's cancel. Isn't that beautiful? So what we end up on the right side is the moles of A over the total moles. It's just a wonderful thing. So that mess I showed you a minute ago comes to this. And we're not quite in a form that we can ultimately use it, but we're getting close. Partial pressure of A over the total pressure is equal to the number of moles of A over the total number of moles of gas that are squirting around in there. I can rearrange, if I take both sides times the total pressure, it looks like this. Both sides times the total pressure. We get the partial pressure of A by itself, and then on the right we have the ratio of moles of A to total number of moles of gas times the total pressure. Now this is getting close to the form that we would use it in. Actually, it is the form that we would use it in. But down there at the bottom is an important way to talk about a component in a mixture. It's called mole fraction. fraction just means the relative number of moles of something to the total number of moles of something. So that little ratio there is the mole fraction. This is the mole fraction. Mole fraction, how many we got of a component divided by the total mole number that we got, period. All right, and the variable we use for mole fraction is an x. So in physical science, if you see an x with a little subscript, they're talking about the mole fraction of what that subscript is. So x sub a means mole fraction of a. So then that little important relationship between partial pressure and total pressure now looks like this. And we're going to work an example, but you need to know anytime you see that x, that's mole fraction, that is the moles of A, just like it says up above, moles of A over total moles. Which is kind of cool. So it means if you want to know how much pressure a component is going to exert, all you do is take its mole fraction times the total pressure. I just think that is so cool, but I'm easily impressed. So let's work an example using that. And I'll go ahead and put it up here. Partial pressure of anything is equal to the mole fraction of that thing times the total pressure. So in this example, we have three gases that are in the common container banging around. We have carbon dioxide, nitrogen, and neon. Unfortunately, notice we aren't given the amount in moles, we're given the amount in mass. So here in a minute, we're going to have to get moles of everything, but we can do that. We're supposed to determine the partial pressure of each gas and the total pressure. Okay. So just looking at it, what I'm going to tell you to do is let's go for the total pressure using total pressure. So let's see, PV is equal to nRT. I always have to write it this way and rearrange it. So the total pressure is equal to the total number of moles times R times T divided by the volume. Okay? We can do that. So that's why I said we need to get, from those grams, we need to get moles of everything. And then once we have this, then all we got to do is take for each of them that number times the mole fraction. Mole fraction of CO2, mole fraction of N2, mole fraction of neon, and knock out the partial pressures of each of those three gases. So it's really not too bad. That's how I would do it. I think that's probably the best way to do it. So let's go ahead and go from grams to moles for each of those. So of course, on a test, you have to tell me how do you come up with the molar mass of CO2. Molar mass of CO2 is 44.01 grams per mole. So if we take the 2.00 grams times 1 mole over 44.01 grams, round to three significant figures, we get 0.0454 moles of CO2. Now notice this is a good example of, we're going to find the moles of three things. So I really think in order to communicate your work, you should write moles of CO2, and then you don't have to worry about labeling CO2 with your other stuff. I think that makes sense. So moles of N2, we're going to start with the mass of N2, which is also 2 grams. So 2.00 grams. Nitrogen is 14.01, so we're going to take that times 2. So 1 mole over 28.02 grams for nitrogen. And we have 0.0714 moles of N2. And then last but not least, neon, simply looking at the periodic table. Its mass, again, was 2.00 grams. Periodic table gives it a decimal number for neon, 20.18 grams per mole. So use the flipped version of the molar mass and then come up with 0.0991 moles of neon. So on the next slide, what you're going to see is what I said, how I would approach this problem. I would basically add these together to come up with the total number of moles. And plug it in here. So, total number of moles looks like this. And we don't do as much addition like this as multiplication division. We need to round according to decimals. Notice that in each of these cases we have, what, 4 decimals? So we're actually allowed 4 decimals in our sum. So actually the total number of moles is 0.2159. And that is going to go in there. So it looks like this. Looks like we needed to fix our temperature, which was 15 degrees Celsius. We add 273, so we get 288 Kelvin. I think that's it. So plugging in, it looks like this, where our N is our total number of moles, 0.2159 moles. Also in the numerator is R, 0.082058, and units of R are liters, atmospheres, per mole Kelvin. And then we also need to plug in our temperature, 288 Kelvin. In the denominator, we put our volume, which was 5.00 liters. Looking at what cancels, looks like moles cancel, kelvins cancel, liters cancel, and we're left with units of atmospheres in the numerator, which is great. 3 significant figures because of the volume and the temperature, so 1.02 atmospheres. And actually, the original problem said, what's the total pressure? So there you go. There's the total pressure. Now, to get the individual pressures, we could go back to this same thing and plug in the individual moles. But I think it's easier to use the mole fraction times the total pressure. So that's actually what you're going to see done on the next few slides. But the other would work, in case you have a brain fart. So to get to the CO2, we need the mole fraction of CO2, which was the moles of CO2, 0.0454. And I'm just going to kind of leave that unitless because the moles are going to cancel with each other. 0.0454. The total moles, that 0.2159 that we used before, times the total pressure, 1.02 atmospheres. Round to 3 significant figures, I get the partial pressure of CO2 is 0.214 atmospheres. Now, intuitively, don't you suppose when we get all 3 partial pressures up here, they should add up to what? That 1.02 atmospheres, shouldn't they? So let's see what the next partial pressure is. The next partial pressure was for nitrogen. So we got 0.0714 moles of nitrogen divided by the total pressure, total number of moles, 0.2159 moles. Moles cancel. Rounding 3 significant figures, I get a partial pressure for the N2 is 0.337 atmospheres. And for you shortcut people, it seems like you should be able to get the third one by difference. And you can, but I would suggest just going ahead and applying this. So for the neon, we had 0.0991 moles of neon. Total moles, again, 0.2159 moles of gas. Here's your mole fraction. The total pressure, 1.02 atmospheres. Rounded 3 significant figures, I get 0.468 atmospheres. So yeah, add them up and see if you get 1.02, which you should. Okay, are there any questions about this one? I'm going to do one more problem. Sit down for this one too. Okay. Let's see what we got here. We got a lot of words is what we got. Okay. So it says I have 150 grams of this, this dimethylhydrazine. So I'll find my dimethylhydrazine, write down 150 grams. It says that we're going to have X, the other reactant's going to be in excess, which is nice. Makes our life easier. And it says that, notice we have 3 product gases, and they're all going to be collected at the same temperature. So let's see, maybe I'll do this. I'm going to put all 3 of these, and I'm going to say T is equal to 27 degrees Celsius. And I'm going to say that they are going to be hanging out in a container, that's a big one, 250 liters. So V is equal to 250 with 3 sig figs liters. So we're supposed to come up with the total gas pressure. So PT is equal to question mark. Okay, and we're supposed to knock out the partial pressure of one of the products. P sub N2 is equal to question mark. Okay, now we did stoichiometric calculations. You guys figure based upon this mass, we can get to the moles of all 3 products, right? In theory. Okay. You can get to the moles of N2 and the moles of H2 and the moles of CO2, right? Okay. And then you'll have the total number of moles, and you can get to the total pressure from there. And I think that's how I do it. Okay, so this is, in order to get to moles, we're going to have to convert the mass of the reactant to moles. So this is the molar mass of that reactant, the dimethylhydrazine, which is really nasty smelling stuff. Okay, so if we go ahead and take our mass of the reactant that was given, the limited supply, 150 grams, use the molar mass to get to moles. So we have 2.50 moles of the reactant. Okay. Seems like there's a... Okay, yeah, now I was like, what twist is there? And here's the twist. Now you wouldn't have to do it this way. But do you see the stoichiometry is actually 1 mole of the dimethylhydrazine, the CH3 quantity 2 and 2H2, will form collectively 3 plus 4 plus 2, or 9 moles of gas. Do you buy that? Does that make sense to you? I mean, we could go individually, the 3, the 4, and the 2, but collectively there's 9 moles of gas produced. And again, this is another place where if you didn't want to apply this kind of shortcut, you wouldn't have to. I think it's kind of a shortcut. Well, if you buy that, then we can put as our first term 2.50 moles of the dimethylhydrazine over 1, and then just insert that ratio, 9 moles of gas produced for every 1 mole of dimethylhydrazine. And bada boom, we quickly have the moles of gas that were produced. Now you could go each individual gas and you'd get the same answer. So if you do that math, rounded to 3 significant figures, our N sub T, our moles of gas produced, are 22.5. That's your NT. Actually, this is a very nice shortcut. So if that's our total moles, we can get to our total pressure now. One of the things I don't like on this slide, and a few slides are kind of like this, is that we are talking about the total pressure using the total moles. I think that's significant. We had to fix our temperature by adding 273 to 27 degrees Celsius and getting a Kelvin temperature of 300 with 3 sig figs. And so here we go. Our total pressure is the total moles, which is 22.5 moles, times R, 0.082058. Units of R are liters, atmospheres per mole Kelvin, times 300 Kelvin, divided by the common container they're all swimming around in, 250 liters with 3 sig figs. So that gives you a total pressure of 2.22 atmospheres, which was the first question. The second question, we're going to go ahead and apply this sort of approach. We know the total pressure, we just have to take the mole fraction of the nitrogen gas to get the partial pressure of the nitrogen gas. So here's how that looks. Okay. Notice that out of all of the moles of gas produced, 3 of the moles were nitrogen. So actually that is your mole fraction. So the partial pressure of nitrogen is 3 to 9, which is the mole fraction, times the total pressure, which is that 2.22 atmospheres. Rounding to 3 significant figures, I get 0.740 atmospheres. We could do a similar thing for the H2O gas and the CO2 gas if we wanted to. But why? So these will also be due on Wednesday, 60 and 61. And these are also out there. They're out there somewhere. These are, I'll also push out on Twitter, and they look like, but I won't belabor going through them right now. The hints, if you want to take a look like this. For again, we're dealing with gas mixtures. This one, they're kind of similar to the examples we worked in class, so if you wrote those down, that should help. That's the first one, and this is the last one. This one's a little more interesting. But if you read my hints kind of from left to right, you should be fine if you want to use them. Okay? So any questions? I guess that's it. See you on Wednesday.